Okay, welcome to the second session of this course. Today's topic is how to implement A-core RISC-V microprocessor with the digital flow. And the main thing that is different in this exercise is the fact that we are going to implement macro blocks into the design. So let's see. So the result should look something like this. I hope that I have run the flow. The flow takes a bit longer than the previous one, so I can rerun it during this session, but I can demonstrate the actual operation with a bit different design, or I can just use the already synthesized version. If this is okay, then I will do that. So this is how the processor will look like in the end. And again, as in the first exercise, you see the IOs at the top and IOs at the edges and IOs at the bottom, but you see also memory blocks. And these memory blocks are like very simple implementations of generic memory. You can utilize these blocks in your own PIC design. There is a 12-bit variant and 8-bit variant, and the widths are sufficient. If the width or size doesn't match your needs that you need in the PIC, just use it. Just leaves part of the address space like unused. Should be fine. The main idea is that you can implement your PIC microcontroller by using these memory blocks. You place those memory blocks in the layout and they are used as macros. And that's what I'm like teaching on this second exercise. In general, when you're doing digital designs, you have blocks that do something. Most often in digital designs, those are memory blocks. They could be analog macros, D2A converters, ADCs, power controllers, whatever macros, but they are placed in the design and they are routed automatically. So this exercise kind of shows you how to do that. And how it differs from the previous exercise is that there is differences in one file. So this is the result of the flow. And now I can show you how we end up to this point. So I will close this. And we can check which parts of the configure file have changed. This is also part of the second exercise that you should compare the compare files or you're instructed to compare files of the first exercise and second exercise to find out the differences. But basically, what is different is, okay, here, of course, the name of the design is different. Then we define that we are using dual port memories. This is not mandatory, absolutely mandatory for your pick, but only the dual port memories are available for this process, and this is used to choose them later on. Yes, this is the trick. You need to define 2 analog macros. You can actually just copy this definition to your big project configure file later on, and this will kind of bring these macros into your use. Then you can use them in your VHDL source files as they would be entities. So the description of these files are Verilog, but you can use them as they would be VHDL entities in your VHDL code, because most of the RTL synthesizers, they support multi-language implementations. You can implement or use Verilog modules as they would be VHDL entities, or VHDL entities in your Verilog design as they would be Verilog modules. You just map the IOs. So these memories can be used, but you need to add them here as analog macros, and the flow configuration will implement most of all the files to in Genus and Innovus for you. Then this is the part specific to this A-core implementation. We have defined that we do memory mapping here, and now we check if we are doing memory mapping, we are running for this particular instance of A-core this compilation procedure. Your pick does not have this compilation procedure and doesn't use this chisel memory mapping. But this results to 2 Verilog configuration files added to the RTL path, and we add those to the list of the Verilog files. So this does the Verilog compilation of the chisel and adds the Verilog files to be available for the flow to be used. If there are some files missing in your case, if you don't compile all the VHDL files, or if you don't compile the memory models, then you will get an error. These are the only changes that you need in source file manipulation. Then, of course, we need to change the size of the design a bit compared to SPI, which was quite small. We have now increased the area with some 200 microns per dimension. And then, as we remember from the last lecture or session, we need to modify the SDC file, which defines the clocks. So clock signaling and IOs are always design dependent. So this design has different clock naming and IO naming than the previous design. So we need to redefine the clocks or define them differently. We have also changed the clock frequencies a bit. And then also all these IO names you need to redefine. Check what are the names of the IOs in your design and then modify them. But for this A-core, they has been changed now. So after the configure is ready, we can, let's see. Okay, this is not related. Yeah, One thing added also are these timing libraries. These you need to add also in your design. So you can copy these configurations directly from this project. This adds the timing library models for these memories. Basically, those timing libraries are non-existent. They just are placeholders for the timing libraries. They define default load for the drivers that are driving the inputs of the memories, and they provide the rise time of the signal at the output of the memory block, which are used in timing analysis, but they don't model the propagation time through the block. So it is assumed to be very fast. Okay, so those are the configurations you need. I will still check the part. Yes. Depending bit on from which template project you start designing your big project eventually, consider setting this to true if it's set to false. This causes your flow to barf an error or return an error code if you have undefined instances in your design, meaning that you are missing some BSDL or Verilog file. And how I find this out was that I had a problem in memory block configuration when I was setting up this exercise again for this course this year. And I ended up to clock tree synthesis phase before the flow failed. And the reason was that I did not have one of the memory blocks defined in the design. And this was set to false, and it just noticed that, okay, I have undefined block, and it sees how it is connected, but it just don't have any definitions for that block. So it creates a placeholder Verilog module for it. And it went on, but because there is nothing in that block, it can't proceed after a certain step, and that step seems to be clock tree synthesis. So remember this when you are doing your peak designs. I think I changed it to the template. Okay, so that was the configure, and then now I have run configure and then make up to, let's say, floor plan, which I needed to redefine a bit. This template actually runs through, so you don't need to modify it. But if I open now the floor plan phase as asked in the exercise issue, it goes like make debug Innovus Okay, now I have Innovus here open, then GUI shell. And then I will open the floor plan script, which is the most interesting part here. So again, as in the previous exercise, I start by pasting this portion. Sorry, forgot one step. I need to read db this pre-fb.enc, which is saved in the very early phase of the floor planning. And then I will paste there this beginning part of the file. Okay, now I should have that one. Then I don't save the pre-FB because I just read it in, and then I keep on pasting the commands. Good. Then we can take a look at what's inside the place IOs. I have again used this automated direction definition if clause, and then I just assign the ports by using those layer definitions here. So it defines left and right pin layer to be either metal 4 or metal 3, depending on direction of metal 3. But now the IO names here are the ones used in this A-core processor. So in case you are doing your pick, you need to modify these two. Let's see what happens. Oh. Okay. We have the pins in place. It seems that we do not place one pin. We need to. Which pin is that? IOGP01. I didn't do it. Because I haven't pressed enter here. Now they are gone. So now all the IOs are placed. I should probably add now it's easier to paste. So we have IOs in place, and then we can go on with this. Okay, let's see what's there. Yes, this is the place where you actually place the memory macros. And this is the command. So it's an instance name, X and Y coordinates rotation, and then the placement is fixed, which means that during the placement of the standard cells, it is not allowed to move this block in the design. Usually you want to fix the placement of your macros. How to find out what are the actual names of your memory blocks? You can check your Verilog netlist, for example. There are inside some module, there is an instance of RAM0 with instance of RAM0X with instance of MEM0 inside it. And how you can find those, there is a command in Innovus, get db insts. So if you know any part of the name, you can check if it can be found with this get db insts, and then using wildcards. You can also, I know that there is in Verilog there is an instance called progmem, so I can check if I can find that. Yep. And let's see what else there could be. RAM. Yeah. So it seems that this mem0 is common denominator for this. So that should, it returns progmem instances and RAM instances. So with this getDB inst, you can look at the instances of your design. And now this is a bit risky, but you get all the instances with this. So it works now for this reasonably small design, but if you have millions of instances, it may result in problems. So now we are ready to place them. There's also example how to echo messages on the command line in your script. So this is handy if you want to do debugging, and if you want to check errors, you can use this to put out something if you want to see that what is happening during your execution of the scripts. Let's place the instances. No errors, which is good. And now the instances are there. Some bit more generic instructions on how to place instances. Fastest and the most convenient way is to just define the coordinates and place the instances to those locations. A bit more advanced methodology, which is actually quite nice if you don't know what will be the eventual location of those modules, you can use relative placement, for example, so that you can place the instance with certain offset relative to the lower left corner, and then all the rest of these relative to position of this corner. And you can get with these getDB commands, you can get those locations or coordinates of the lower left corner of any instance placed in the design. So you can use that kind of approach to construct your floor plan. It's a bit more tedious task because you need to figure out what those commands are and then write a bit more complicated script, but eventually it pays off. For example, what I did, there is another project inside this project that you are using as a template. So it is this memblock. And in that, I have this generate floor plan file, which places one memory block inside it. And how it does it is that this is actually an example of how to calculate the locations. And this places one memory block always at the center of the chip. And why I wrote it this way is that when I do the process setups, I don't know what will be the eventual chip size, but it must be larger than the memory block. And there must be some place for standard logic around it, so the safest place to put the memory block is at the center location. So I just calculated the coordinate of the center location. Then I calculated the memory macro width in X direction and Y direction by getting these widths from the actual macro cell, and then calculated locations by using those variables. The other script that I have used in the past, I don't have example of it, but eventually I didn't know how many memory blocks I had, but I knew that there like will be many of them. So I wrote a script that places the macros with equal spacing in Y and X direction within a given area, which is very handy. You can define in your design that, okay, this is the area that I dedicate for memories. Regardless of how many blocks I have, they will be spread eventually inside this area. And it requires some tickle scripting, but eventually it was quite handy because the number of those memories changed often, and I didn't know how many eventually I was going to have. So that kind of saved a lot of work from me. Because every time, you should probably just keep in mind that every time you write something like hard-coded number, there is a chance that you need to change every one of them eventually. So if you can automate something with using variables derived from somewhere, it's beneficial. Okay, but let's get back to this exercise. So now we have the memories in place, then the rest is as it was with the first exercise. So this place for ports is actually empty. It would place the path cells, but we don't have them. So let's go there. The file contains only comments. Then this defines the routing rules. Just as a reminder, it defines that we use double width and double spacing for clock signals. And this finalized floor plan does just some snapping to grid, nothing very fancy. Usually it does nothing. Then we can write the prestripes.enc, because if you need to iterate your stripe power routing, like rings and stripes here, you probably want to start from this point. So we can rewrite that just to see if it still works. Okay. And then we get to this rings and stripes phase. This is actually, I think this is the same file as in the previous exercise. It is so well parameterized that you don't need to change it. And also this memory blocks doesn't require any kind of a special arrangement for connecting the supplies, so we can just use standard way of creating power routing. And now we can see if we zoom here. See if I have those cell and layer, and let's start with, could it be metal 4? No. put those pin shapes invisible. See that? Because they are there. Okay, so now if I put pin shapes visible and all the layers visible, let's see, here is the pin for signal and here is the pin for VDD. And now let's, if I these are the, sure those might be, those are signal routes. I need to find the VDD pins. Very difficult from this mess. There they are. So these are the supply pins. They are on metal 3 and metal 3 is horizontal in this case. So let's see if I have metal 4 somewhere. And then that one. Yes, that was lucky. This is how the supplies of the memory blocks are connected. So when you lay the stripes over the block, it automatically adds vias to the crossing of the corresponding supply pin and the corresponding supply net, and it creates this kind of a via array that connects to that. When you are doing real designs, these are the things that you should like visually check a couple of first times when you are running the flow, so that your like supply connections are reasonable. There is also this tool called Voltus that analyzes the strength of the supply connections and like reveals if something is off, but we haven't used that. So like visual checking is always safe to check that if the methodology that you're using is doing what you expect it to do. Then the other place that you could check, if I did not mention it on the first lecture, is this edge. So if I put metal 1 visible, let's take metal 3, metal 4, and metal 2 visible, and then via in between. You should see that these metal lines that feed in the supply to actual core are connected to these metal 2 lines, and then that they are connected also to metal 4 stripes that go over the design. Let's take a point where those are. So we have metal 1 connection up to layer metal 4. So all our supplies are well connected and standard cells have decent power. Okay, but as you can see, when you put all the metals visible, like nothing really is visible. So Let's see. So we created a power routing. And then there is a final steps remaining. Just save the final version of the floor plan so you can get back to it if you wish later. Like this. And after that, rest of the steps should go from the file design config.tcl. If we open that, it's in flow scripts design config.tcl. So what we did just was this file. So the following steps will execute these files mentioned in this file. You can paste these one by one, or you can just like here run this make from oops. Still in Windows. So this re-executes the floor plan step and then everything after it. Oops. I have run this once, so I can force it. So this make flow force is something that if the final file provided by the flow, which is one GDS file used by later steps of the design construction, if that file exists, the make file checks the existence of the file, and if it exists, it will not rerun the flow. But with this force flow, you can force it to run it again. Okay, any questions at this point? I will help you through this during this session, so don't worry about that. This is just a demonstration what to expect and how to place the macro. Misma. How to define the dimension? Usually it goes in a way that you guess something, then you find out if it's way too large or if it's way too small, and then you need to modify. But these design dimensions are given in, let's see, in configure file. Yeah. Or you can check where these variables are used in your flow. Like this is handy command grep-rn grep-rn string and all the files you want to check, and it tells you where it is used. So you should check the file create floorplan.tcl that uses the variable. So that is a place where you can define the dimensions of the chip.
In the first exercise, were we supposed to also run the configure with our PHDL types, or just how we would implement?
In the first exercise, I instructed to use branch VHDL version, which is exactly the same implementation as of the SPI slave as with Verilog, but it should just use VHDL. That is to demonstrate how to include the VHDL files in your design. And by using that information, you should be able to add your PIC designs. But I will still write the instructions for the third exercise issue that tells you how to initialize your PIC project and how to proceed with that. I just haven't done that yet. Okay, so while this is now running, we can do whatever. I can actually stop recording this session and I can help you through the first exercise if you haven't finished that, or if you have, I can debug the second exercise and I will check for Antti why you don't have the issues. So let's see.